Hello and welcome to iPie Maths. This is my first video actually, and I decided to go through some differential equations. Specifically, I'm going to go through using the integrating factor method on these linear ordinary differential equations of order 1. You can see that I've got 3 examples here, and each example is slightly different from the last. Our first example is in the form y dash, which is dy of dx, plus some function of x times y is equal to a second function of x. Like I said, this is exactly like the form here. These two are the same format. This question here is slightly different because I don't have I have a function of x in front of my dy of dx, which I do not want if I want to jump into my integrating factor method. So some rearrangement, some algebraic manipulation is required here. And for this third one, again, it's slightly different because we're going to have to use a substitution to solve it. So I'm just going to jump straight in and go through the first one. If you want to pause the video and have a go, feel free. And play whenever you're ready. But I'm just going to jump straight in. This question, like I said, is exactly in the format we're looking for. We're looking for dy of dx plus p of x y equals q of x. I can see that my p of x is equal to x, and so I can use my integrating factor method straight away. I've got my integrating factor method is e to the power of p of x, which in this case is just x, integrated with respect to x. Hopefully we should all be able to do this integral. We're going to end up with e to the power of x squared over 2. That's my integrating factor. What we do with our integrating factor is we take it and we multiply both sides of our differential equation by that integrating factor. That's actually the reason we forget the plus c, because if we have the plus c here, this is the same as e to the x squared over 2 times e to the c, which is just a constant, which would cancel out because it's a factor. So we don't need it, and we're not going to include it, but that's the reason why. We're going to multiply both sides by e to the x squared over 2. When we do that, we get e to the x squared over 2 dy over dx plus x e to the x squared over 2 y, and this almost difficult to deal with right hand side is going to become a lot easier because I've got e to the x squared over 2 times by e to the minus x squared over 2, which the keen observers will realise is going to become e to the 0. Now this left hand side, this is where we need to use our sort of reverse product rule. I'm going to start off by saying or stating what the product rule is. So the product rule is the derivative of u times v, which are both functions of x. I'm going to have u v dash plus v, or u dash v, like that. And you can see for the product rule we've got our two terms. One of the factors for my first term differentiates to give me one of the factors of my second term, and vice versa. So we can see that if I differentiate u, I get u dash, and if I differentiate v, I get v dash, and they sort of match up in this sort of pattern here. This e to the x squared over 2 differentiates to x e to the x squared over 2, and y differentiates to dy of dx. So you can see we've got the exact same pattern, we've got the exact same relationship on my left hand side as I do with the product rule. So that means we can just go ahead and sort of write this left hand side is the derivative of the product of y and e to the x squared over 2, like that. My right hand side is still e to the 0. Now if I want to solve this, I can just integrate both sides with respect to x. And then solve this by evaluating the integral of 1 with respect to x, which is x plus c. Now we don't forget the plus c. It's important to remember it there. We want to solve this differential equation, which means we want to find what y needs to be. Well, y needs to be x plus c multiplied by e to the minus x squared over 2, or divided by e to the x squared over 2. And we get this here. So that is our answer to the first differential equation. Looking at the second differential equation, like I said, this one's slightly different because I've got a function of x multiplied with my derivative. So to solve this one, we just need to add in one extra step, and that is, well, actually, I'll say pause the video if you want to have a go, and then I'll go through it in just a second. So the extra step is that we just need to divide both sides by x squared. Now, if you're really, really good at differential equations, then you might realize there's actually a shortcut, but I would recommend that you don't try any shortcuts, especially in the exam, especially when you're just starting out. Plus it takes the fun out of it. So I'm going to divide both sides by x squared. I'll show you what the shortcut is at the end, but if I divide both sides by x squared, I'm going to get dy over dx plus 1 over xy is equal to the natural log of x. Okay, well now I know what my p of x is. My p of x is equal to 1 over x, which means my integrating factor is equal to e to the integral of 1 over x dx. The integral of 1 over x is the natural log of the modulus of x, which the e and the natural log, because they're inverses of each other, will cancel each other out, and that modulus is no longer required, so we'll just write it as x. So we're now going to multiply both sides by x, and we end up with x dy over dx plus 1. I'm going to write that 1 there just for demonstrative purposes in a second. You might notice that, well, if I've divided by x squared and then I've times by x, that's just the same as dividing by x. And you might be able to spot that from the start, and if you can, that's great, but if not, don't worry, because I would recommend you do the integrating factor method no matter what. Sometimes you'll do the integrating factor method and you'll sort of go back in a loop and end up back at the start. There's no harm, it doesn't take too long, especially once you get the hang of it. So I can see again that if I differentiate x, I get 1, and if I differentiate y, I get dy of dx. So this is my product rule, so I can write this as d over dx. I take the y, I take the function of x multiplied with my dy over dx, which is just x, and that's equal to x natural log of x. Integrate both sides, I get y x is equal to the integral of x natural log of x with respect to x. This shouldn't take too long to work out. Obviously, if I try and integrate the natural log of x, it's going to become a little bit awkward. So I'm hopefully spotting that integration by parts is relevant. I'm going to need to label the natural log of x as u and the x as v dash. So I get uv minus the integral of v du over dx with respect to x. uv is going to be, u is the natural log of x and v is x squared over 2 minus the integral of x squared over 2, again, because it's v, and u is going to equal, well, du over dx is going to equal 1 over x. And we're going to work out this second integral now. So we've got x squared over 2 natural log of x still. The x's and the x there are going to cancel to give me the integral of x over 2 with respect to x. And then I get x squared over 4. So my integral complete is x squared over 2 natural log of x minus x squared over 4 plus c. Now I want to find y equals not x, y equals, so I'm going to divide both sides by x. I'm going to get x over 2 natural log of x minus x over 4 plus c over x. And for the sake of being as mathematically correct as possible, we're going to say that this is our solution to the differential equation, and we also have that x cannot equal 0. Like that. So that's the answer to the second one. The third one is a very interesting one. It's not too difficult once you know the trick behind it, which I'm going to go through obviously, but if you want to have a go at this one as well, do feel free to have a go now. So if you had a go at that, let's see if you've got it correct. This is one of my favourite types of differential equations because it's almost like a integrating factor question in disguise, because I've got to use the substitution first. So, like I said, we can see that if I differentiate dy over dx, I get d squared y over dx squared, so they are still only a difference of one derivative apart. So that means I'm going to use the u substitution, but I'm not actually going to use u. I'm going to use my knowledge of the fact that I'm going to have to use integration by parts to solve the answer. So I'm going to avoid using u and I'll use r instead. So I'm going to say that r is my substitution, and r is equal to dy over dx. If I differentiate r, I also differentiate dy over dx, which gives me dy, or d squared y over dx squared. And I can replace my derivatives on my left hand side with dr over dx and r. So I get 1 over x dr over dx minus 2 over x squared r is equal to x e to the x. Now I've also picked this one because if you notice, obviously we're not dividing. I mean, you can divide, but obviously we want the function of x there to be 1. So we're actually going to times both sides by x. And that's going to give us dr over dx minus 2 over x r is equal to x squared e to the x. Now my integrating factor here is going to be e to the integral of minus 2 over x dx. Be careful to bring the negative with you. That's a common mistake. I'm actually going to bring the minus out, and I'm just going to look at 2 over x dx, which we should have really brought the 2 out as well, but there we are, done it now. I've got e to the minus 2 natural log of the modulus of x. Doesn't really matter how you go about trying to rearrange this. I'm going to bring the minus 2 into the power using my log rules. And I've gotten rid of the modulus now a little bit earlier, one step earlier, because I'm obviously squaring my value, so it can't be negative anyway. This is going to give me x to the minus 2 as my integrating factor. So that means I'm going to times everything by x to the minus 2. And that's going to give me x to the minus 2 dr over dx minus 2x to the minus 3 r is equal to e to the x, because x squared and e to the x are going to cancel out. Well, this looks good, because now I can see that if I differentiate x to the minus 2, I get at minus 2x, x to the minus 3, and I differentiate r, I get dr over dx. You don't need to do this representation every single time. This is just me double checking that I've done my working out correct. So I'm going to take the r, and I'm going to take the x to the minus 2, that's equal to e to the x. And then to solve this, I'm going to integrate both sides with respect to x. Hardest integral ever, e to the power of x integrates to e to the power of x plus c. don't forget that plus c. Just because we haven't finished yet doesn't mean we don't include it. Next we need to make sure it's r equals, so we're going to write this as x squared e to the x plus c x squared. Now, we obviously introduce r is equal to dy of dx, so we need to write this as dy over dx is equal to x squared e to the x plus c x squared, like that. Now we need to find y, and this is where you might be thinking, oh, this is going to take us a while. This is going to have to use integration by parts twice, which is not necessarily the quickest calculation or computation to do, but hopefully it won't take us too long. We're going to have u is equal to x squared and v dash is equal to e to the x. So I'm going to have uv, which is x squared e to the x, minus the u dash v, which is going to be, I'm going to put the 2 out the front. This I can work out straight away. This is just going to be add 1 to the power, divide by the new power, is c over 3. I'm going to write that as c1, because when I eventually do this integral, I'm going to get a second constant, which I'll call c2. So this is a constant 1, so it's c1. If I do c divided by 3, that's still a constant. So I've got my x squared e to the x minus 2 lots of, I've got to use my integration by parts again. I'm going to have u, have v dash, so I've got uv, which is x e to the x, minus the integral of u dash, which is 1, v, which is e to the x, plus c1 x cubed. X squared e to the x minus 2x e to the x, negative and negative makes positive, so I've got 2e to the x plus c1 x cubed, and then c2 on the end. So I have y is equal to x squared e to the x minus 2x e to the x plus 2e to the x plus c1 x cubed plus c2. So I hope you found that useful for some entry-level integrating factor questions. Please let me know if you have any questions in the comment section. I'll try and answer them on my next video. And like I said, I'll do a proof as to why the integrating factor method works and what it looks like in general in another video. Thank you for your time. Please like, share, add any sort of comments you think would make the videos better. And I look forward to see you again in the next video. Bye for now.